I'm talking about also results that trying to work with Paul about excluding paths and antipaths, and I'll tell you what I mean. So this is motivated by the Erdős-Heinel conjecture. So we've been studying the properties of graphs with certain induced subgraphs excluded for a while, and we're trying to prove some structural results maybe, but there's actually a conjecture that says something about all graphs with a certain induced subgraph excluded. It doesn't say anything about their structure, but it does say something about does conjecture a certain property. So that's the Erdős-Heinel conjecture, and what it says is that if I give you a graph and I promise that some little graph is excluded as an induced subgraph, then the big graph has either a surprisingly large clique or a surprisingly large stable set. So surprisingly large means the number of vertices to some power, right? I take an n-vertex graph and I fix some graph H, and I promise you that this n-vertex graph does not contain H as an induced subgraph. Then the n-vertex graph has either a clique or a stable set, which is n to some power, where the power depends on H. Okay, so this is this is interesting, because if I didn't tell you that I excluded H, if I was just allowed to look at a random graph, then the expected size of the biggest clique and the biggest stable set would be log the number of vertices. So really, this conjecture says something dramatic happens to the graph if you exclude an induced subgraph. All right, so let me say that a graph H has the Erdős-Heinel property if the conjecture holds for it. So the Erdős-Heinel conjecture says every graph has the Erdős-Heinel property, but right, sometimes we know it and sometimes we don't. Okay. So it's hard. Not very much is known. Let me tell you a little bit about what's known. So first of all, in the same paper where Erdős and Heinel made this conjecture, they proved a weaker version of the theorem. They proved that if I exclude H, then there's a clique or a stable set. Oh, look at that. There's a clique or a stable set of this size, right? So what I would like is e to the c of h log n, and they have a square root in here. Right? If I didn't have this square root, that would be precisely this conjecture. But they got it with a square root. So then you can prove that all graphs on at most 4 vertices have the Erdős-Heinel property. If I exclude anything on at most 4 vertices, then I get a big clique or a big stable set. And that's not very hard. You can also prove that the bool, it's this graph, 5-vertex graph, has the Erdős-Heinel property, and that's pretty hard. That's sort of a real theorem. So basically, that's all that's known. I'm cheating a little bit because there's an operation that you can perform on 2 graphs that have the Erdős-Heinel property and get another graph with the Erdős-Heinel property. So you can construct an infinite family of graphs all with the Erdős-Heinel property, but that's by, I'll talk about this a little bit later, but that's by sort of, it's kind of a cheat. You're not proving anything new, you're just applying this operation. So 2 and 3 are the only graphs for which the Erdős-Heinel conjecture is known kind of honestly. Okay. So it's hard. Let me say, right, so the Erdős-Heinel conjecture tells me there are big cliques or big stable sets, so I want to have a word for it. I'll say a graph is delta each if it has either a clique or a stable set, which is the number of vertices to the delta. Right, it's the same concept we already saw, just I want to have a word to describe it. And so, again, to say the Erdős-Heinel conjecture in this language, for every graph H, there's a delta, so that if H is in every graph with H excluded, is delta H. Okay, so far I've reformulated the Erdős-Heinel conjecture sort of in simple ways, but 3 times. I had the original conjecture, then I said every graph has the Erdős-Heinel property, and then I said for every graph there's a delta, so that if G doesn't contain this graph, then G is delta each. Now I'm going to give you another reformulation, slightly more non-trivial one. So we had delta each, now let me define alpha narrow. Okay, so what's alpha narrow? Alpha narrow has something to do with functions functions on the vertex set of the graph. So the general idea is, if I give you a function and I promise that it's not too big on any perfect induced subgraph, then it's not too big on the whole graph. That's what so a graph is alpha narrow if it has this property. Every function that's not too big on every perfect induced subgraph is not too big on the whole graph. So now let me say more precisely what I mean and what alpha has to do with it. So let me say a function is good. So it's a function from the vertex set to the non-negative reals. Actually, I can just take the 0, 1 interval. That's good enough. So this function is good if it sums up to at most 1 on every perfect induced subgraph of G. What?
Perfect means the graph is
a graph is perfect means the chromatic number, the clique number is the same for every induced subgraph. And now I'm interested in induced subgraphs of G that are perfect, right? That are perfect graphs. Okay, so here it is. So that's what a good function is. Now G is alpha narrow if for every good function, right? For every function like this, if I look at its alpha powers and I sum it over all vertices of the graph. So this is kind of important. This should be G. This is not P. I'm sorry, otherwise this is nonsense. So I sum the alpha powers over all vertices of the graph, then that's at most 1. Right? So I take a good function, the graph is alpha narrow if the sum of alpha powers on the whole graph is at most 1. And so here's another conjecture. For every graph H, there is an alpha, so that if I exclude H from a big graph, then the big graph is alpha narrow. Right? So the Ehrlich-Heilman conjecture said it's delta reach. Now I'm also conjecturing it's alpha narrow. Well, turns out it's the same. So the Ehrlich-Heilman conjecture and this conjecture are actually equivalent. So let me try and explain the equivalence to you. So basically, I need to prove that there's some translation between delta and alpha, so that delta reach and alpha narrow is the same. So okay, so suppose I have a graph and it's alpha narrow. Let me show you that there's some delta for which it's delta reach. All right, so I claim if I have an alpha narrow graph, then it has a big perfect induced subgraph, a big induced subgraph which is perfect. How big? Well, this big. The number of vertices to the power 1 over alpha. And that's because, so let K be the size of the biggest perfect induced subgraph. Then if I take a function which is f of v equals 1 over k for all vertices v. Well, that's a good function, right? All perfect graphs have size at most k, so that's a good function. Now, my graph is alpha narrow, so that means the sum of f of v to the alpha is at most 1, which, now what is this? Well, that's just n divided by k to the alpha, right? I have n vertices, the function is 1 over k on each of them, so that's at most 1, but that means exactly what I said. That means that k is at least n to the power 1 over alpha, right? So this is exactly that. Okay, so I give you an alpha narrow graph, then we know it contains a big perfect induced subgraph, this big. Now the second observation is, if I look at a perfect graph, then, so perfect graph with t vertices, then either there's a clique of size square root t, or there's a stable set of size square root t, because I can cover all the vertices with omega stable sets. Okay, so, but that's good for me, right? I had, I know that I have a perfect graph which is this big, and then I know that either I have a stable set which is this big, or I have a clique which is this big, right? Just by looking at that perfect graph. And that means the graph G is 1 over 2 alpha reach. So if a graph is alpha narrow, then it's delta reach for this delta. So in the other direction, I'm not going to show you all the details, but I'll tell you the idea. So suppose I have a delta reach graph. So G is delta reach. And now, so I want a little bit more. I want to say all induced subgraphs are delta reach. G and all its induced subgraphs are delta reach. Right? And I want to prove that G is alpha narrow. All right, so let me look at a good function. So that means it sums up to at most 1 on every perfect graph, and I want to prove that, somehow not too big on all of G. Well, I claim I can't have too many vertices where f is big, where f has a big value. Why? Because if I did have a huge set of vertices where f of v is big, then this huge set would contain, a relatively big subset which is perfect. And that means, right, by delta each. In fact, it would contain a relatively big subset which is either a clique or a stable set. But then, f of v is supposed to sum up to 1 on this subset, and yet it's a big subset, and these values are big. So that's the idea, and then you make the numbers work. Okay, so alpha each and delta narrow is the same if you close it under reduced subgraphs. Okay, so that means, if I'm I can be trying to prove either of the two conjectures, either this or the Erish-Heilland conjecture, and I can switch at will, and sort of things work a little bit nicer. Okay, so now let me tell you about an operation. Remember I said there's an operation so that if you take two graphs with the Erish-Heilland property, then I get another one with the Erish-Heilland property. Well, this is the operation. So it's a substitution operation. Probably most of you have seen it. So I take two graphs, a graph H1, and H1 has a special vertex, my favorite vertex, right? So there are the neighbors of this vertex and the non-neighbors. And I take another graph called H2, and then I replace this V by a copy of H2. So I build a graph like this. So now I have a copy of H2. It's adjacent to everybody in H1 who used to be a neighbor of V. It's non-adjacent to everybody in H1 who used to be a non-neighbor of V. And that's called that I substituted H2 for V in H1. So I'm going to write it like this. And so another bit of language. In this case, I will call this a homogeneous set in H. So a homogeneous set simply means a set of vertices so that everybody with a neighbor in it is complete to it. So if I did substitution, then I produced a homogeneous set. Okay. And then the other way around. If I have a graph with a homogeneous set, then I could build it from smaller graphs by substitution. All right, so a theorem I already mentioned to you. If two graphs have the Erish-Heilland property, then anything I get from them by substitution also has the Erish-Heilland property. So let me show you the idea of the proof of that. So I have my three graphs. I have H1 with special vertex V, and I have H2, and then I have H. And let's say I know that H1 has the Erish-Heilland property with a constant delta 1. So every H1 free graph is delta 1 rich. And let's say H2, I have the property with delta 2. Every H2 free graph is delta 2 rich. And I'm trying to show that there's some delta for which the conjecture holds for H. Well, the thing is, so here's my big graph G, and it's H free. But so I can assume that if I take a relatively big subset of G, relatively big meaning n to the delta over delta 1, then it contains a copy of H1. Why? Because suppose it didn't. Suppose this subset, this subgraph, did not have a copy of H1. Well, let's just apply what we know about H1, right? There would be a clique or a stable set of size n to the delta here, and I'm happy. And similarly, if I have a subset of size n to the power delta over delta 2, then I must contain H2. Okay, so now you count. So this tells you there are lots of copies of H1. And then you count how many copies of H1 delete V you can have, and turns out not very many. So that means there is a copy of H1 over H1 delete V that you can extend to H1 in lots of ways. Right? All these guys look like V. And lots of ways means n to the delta over delta 2 ways. But then this guy contains H2, and so I got my graph H back. So that's the idea, and again you can make the numbers work. Okay, so that means if I'm trying to prove the Erish-Heilland conjecture, it's enough to look at graphs H that don't admit homogeneous sets, or graphs H that are the minimal graph I need to think about now doesn't have a homogeneous set. Okay, so now here's another theorem. That's with Molly-Safra. So if I have two graphs that are alpha narrow, and I substitute one in the other, then I get another graph that's alpha narrow. So let me sort of first tell you the moral, and then I'll show you how to prove it. So the first theorem says the little graph I can assume doesn't have a homogeneous set. The second theorem says the big graph I can assume doesn't have a homogeneous set. So if I'm trying to prove either the Ehrlich-Heinel conjecture or the equivalent version with alpha narrow, I can assume, if ever I find a homogeneous set somewhere, I'm done. So let me show you how to prove the second theorem, or the idea of the proof. So I have my graph G1, which is, right, so it's something like this. I have my graph G2, just some graph. And then I look at a new graph called G, where I substitute G2 for V. Okay, and now I'm trying to prove that this is alpha narrow. So I have some good function on this graph, right, some function f, so that sums up to at most 1 on every perfect induced subgraph of this. And I would like to prove that its alpha powers sum up to at most 1. Okay, let me look at all perfect induced subgraphs of this, right? All induced subgraphs of this that are perfect, and then find the maximum. Find one that gives me the biggest sum of f. So let's say k is the maximum of the sum of f of v, where v is in v of p, and p is perfect induced subgraph of G2. Right, I have some function v defined on this. I want to find the biggest, the perfect induced subgraph here was biggest sum of f, and this biggest sum is called k. Okay, so now I'm going to define a function on this graph. I'm going to leave f unchanged in a and b, and I'm going to put k here. All right. Now I'm going to define a new function on this graph. So what I'll do is I'll take f of v and divide it by k. So now I claim three things. First of all, the new function I defined on this is good for this graph. The new function I defined on that is good for that graph. And now the fact that this is alpha narrow and that is alpha narrow will allow me to deduce that this is alpha narrow. So let's see all those things. So what happens here? Well, I need to prove that this new function sums up to at most 1 on every perfect induced subgraph. Well, if I didn't use this vertex, if the perfect induced subgraph doesn't contain this vertex, then it's definitely true. So I only need to worry about perfect induced subgraphs, that look something like this. Well, but then this, this k came from somewhere. It came from this perfect subgraph P of G2. Well, substitute P for this vertex. And then it's a theorem that what you get is the perfect induced subgraph of this. And that means the sum was at most 1. So this guy is good. What about that? Why is this good? Well, that's definitely good because the sum on every perfect graph in G2 was at most k. So that's fair. So this is good and this is good. So now we're almost done. Well, from the fact that this is good, I know that, let me do this one first. From the sum that this is good, so G2 is alpha narrow, implies that the sum of f of v to the alpha over k to the alpha, where v is in v of G2, is at most 1. In other words, the sum of f of v to the alpha, where v is in v of G2, is at most k to the alpha. Okay. From the fact that this is good, I get that if I sum the alpha powers of f here and the alpha powers of f here, and I add k to the alpha, that's at most 1. Right, so let me write it somewhere. The sum f of v to the alpha, v is in A union B, plus k to the alpha is at most 1. That's the second fact. That follows from the fact that this is good. Well, but now let's see, what am I doing here? I'm summing up f of v to the alpha. So I sum them up in A and in B. And here, but when I sum them up here, I get at most k to the alpha. So what I need is precisely that. All right? So that's why the second theorem is true. Okay, so now sort of substitutions are our friend. Okay, let me show you an old theorem, but sort of an easy way that uses at least the second theorem. So remember I mentioned that the bool is known to have the Erdős-Helmholtz property. Well, in fact, what you prove is that every bool-free graph is too narrow, or equivalently, or a quarter each. And the proofs, I'll only show you kind of a high-level proof of this. So the first step is, you notice that if you have a bool-free graph that doesn't contain this. So what this is, it's an odd cycle, and a vertex complete to it, and a vertex anti-complete to it. And I'm not telling you, I don't care the adjacency between this and that, right? So if I have a bool-free graph and it doesn't, and neither it nor its complement contains a thing that looks like that, then you can prove directly it's too narrow. It's not very hard. Let me not show you how, but you can. Now the part that I actually wanted to show you is, or to talk about, is if you do have that. Well, if you do have that, then you can prove that there is a homogeneous set in your graph. Then you can prove that your graph is obtained from some smaller graphs by substitution. Well, now I'm trying to prove, by induction of the number of vertices that all bool-free graphs are too narrow. Okay, here's the size I'm working with now. If it doesn't have, if neither it nor its complement has a thing like that, then somehow I know it by different methods. So I can assume it does. But then it's obtained by some substitution from smaller graphs. And since I'm doing induction, I know the smaller graphs are too narrow, so my graph G is too narrow. Right? That's the theorem we just proved. So that was the idea of that theorem. And okay, so there was a nice idea, so we tried to use it again. And so this is what this talk is about, using it again, but harder.
So this is kind of splitter then, if you have that graph.
Yeah, right. That's right. Okay. So, all right. So I said the Erdős-Helmholtz conjecture is hard. Well, let's think about something easier. Let's instead of thinking about a single graph having the Erdős-Helmholtz property, let me think about a family of graphs having the Erdős-Helmholtz property. So instead of excluding one graph, I'm going to exclude a whole family of graphs. So I'll say a family has the Erdős-Helmholtz property if there is some delta that depends on this family, so that if I look at an n-vertex graph that's F-free, that means it doesn't contain anybody in the family, right? As an induced subgraph, then my graph G has a clique or a stable set which is this big. All right, and so now I can ask, try and prove that, right, the Erdős-Helmholtz conjecture says every family of size 1 has the Erdős-Helmholtz property, but you can sort of try and do special cases for bigger families F. Okay, so let me tell you the two kind of main results of this talk, the two new theorems in this talk. One is if I exclude the 5H path and its complement. So in this talk, P sub I is a path with I edges. So the first theorem is that if I exclude a 5H path and its complement, then I get a big clique or a big stable set. So in other words, this family has the Erdős-Helmholtz property. The second result is that if I exclude a 6H path and the complement of a 4H path, so the same thing but asymmetric, then again that has the Erdős-Helmholtz property. All right, so now let me talk about the proofs. So, okay, let me erase something and then talk about the proofs. Oh yeah, it's track and roll. I knew that. Okay, so I want another definition. we understand what it means for a graph or a family of graphs to have the Erdős-Hellman property. Now I want to define the same thing, but with respect to some other class of graphs. So let me say, if I start with a class C of graphs, a family has the Erdős-Hellman property with respect to this class if every graph in the class that doesn't contain any member of this family has a big clique or a big stable set. Right? So it's not the same. For example, if I give you the class of, so if C is the class of graphs, C is the class of graphs that have no induced cycles of length at least 7 in the graph or in the complement in G or G complement, or I should say G has no, oh, okay, close enough. So no cycle of length 7. Well, then C5 has the Erdős-Hellman property with respect to this class C. Right? Because why? Well, if I take some graph here and also tell you it doesn't contain C5, then it's perfect. So it has a clique or a stable set of square root the number of vertices. But of course, in general, if C is the class of all graphs, then I don't know how to prove that C5 has the Erdős-Hellman property. Right? The conjecture is that it does, but I don't know it. All right. So having the Erdős-Hellman property with respect to some classes is easier than having just the Erdős-Hellman property.
So you exclude all graphs in F, right?
Yeah, you exclude all graphs in F. Mm-hmm. Right.
So the H is typo.
What they do?
Every H.
Yes, it's a typo. It should be curly F-free. Thank you. Okay, so that's what it means for a family to have the Erdős-Hellman property with respect to a class. Now, remember we said the Erdős-Hellman property is closed under substitutions. So having the Erdős-Hellman property is closed under substitutions. Well, first of all, so this theorem strengthens it in two ways. One is if I have a family and another graph, a family with the Erdős-Hellman property and some graph with the Erdős-Hellman property, then I can substitute this graph into everybody in the family. That would give me a new family, and that new family would have the Erdős-Hellman property. Right, so that's one strengthening. The other one is I can also do it all with respect to a fixed class C. All right, so substitution is so Erdős-Hellman property for families with respect to a class is closed under substitution. Okay, and that's going to be useful and important. All right. Oh, and by the way, the proof, so it's a kind of a two-way strengthening, but the proof is basically exactly the same as for two single graphs with respect to the class of all graphs. Okay, so now let me show you a little bit about how to prove the two theorems. So first of all, I'm thinking about excluding a 5H path and its complement. Well, with respect to this class, I guess I don't need to write it, it's all there. With respect to this class, C5 has the Erdős-Hellman property. Why? Because if I don't have a 5H path and I don't have a 5H antipath, then I don't have any holes or anti-holes, so any induced cycles or complements of anticycles of length at least 7, and when I exclude C5, everybody is perfect. So C5 has the Erdős-Hellman property with respect to this family. That means if I take C5 and I substitute a copy of C5 for each of its vertices, that still has the Erdős-Hellman property with respect to that family. Right? I'm allowed to do it once and then I'm allowed to do it again and so on. So that's this graph Q. So now here I'm trying to prove, that some graph in the family is delta each for the appropriate delta. Well, I can assume it contains the subgraph Q, because otherwise I would know there is a big clique or a big stable set. Okay, here we go. So now we're going to grow it. I know it contains a thing that looks like this. Now I'm going to grow it under some axioms. So what the axioms are, I have 5 sets. Right, V1 through V5, the consecutive ones are complete to each other, non-consecutive ones are anti-complete to each other. Plus, I want the rule that each of them is what we call tough. So let me tell you what tough means. So I said it's tough if for every partition, so it's an ordered partition, it has parts A and B. Either there is a 2H path starting in A and otherwise contained in B, or there's a 2H antipath starting in B and otherwise contained in E. So a set of stuff is for every partition, either I have this or I have that. And you can check that C5 is stuff. If I start with C5, so right, I started this structure by just having each of VI be a copy of C5, you can check that they're tough. Okay, so now I've grown the structure maximally, and now I start seeing how other vertices can attach to it. Well, if at least one of them, at least one of the sets is a homogeneous set, then I can win by induction, right? So I can assume none of them are. So for every set, there's a vertex that's mixed on it. And then, so you start thinking about what this vertex can look like. It's a little bit hard, so let me just show you the first step. So here's my first set. There's some vertex mixed on it. Now, so far, everything is invariant after taking complements. So here's the vertex. It's mixed on this guy. Mixed meaning has both a neighbor and a non-neighbor, right? So violates it being a homogeneous set. So I can assume, right, so I'm going to, take this set and look at the partition into neighbors and non-neighbors of this vertex, where I can assume what I get is this, right? Because if what I get is that, then I'll just take complements. So this vertex, so there's a 2H path doing that. So in other words, there's a 3H path starting here and otherwise completely contained in this set. Well, then I claim this vertex is not mixed on the union of these two sets. Why? Because suppose this vertex had both a neighbor, and a non-neighbor in this union, well, I can assume it has a neighbor in one and a non-neighbor in the other, but then that's a 5H path. 1, 2, 3, 4, 5. So a vertex like this, it's either complete to both of those or it's anti-complete to both of those. And 25 steps like that later, you can prove that for at least one of these sets, nobody is mixed on it. Okay, so that's this theorem. Now let me show you the other theorem, which is similar. So the other theorem has more steps, but each of them is easier, so I'll be able to show you some of them completely. Okay, so what we're trying to do here is so look at the class where a 6H path and the complement of a 4H path are forbidden, and prove that there's a big clique or a big stable set. So the first step is proving that C7 has the Erish-Heilman property with respect to this class. So, all right, so I need to think about this now, right? I'd like to prove, so proving that C7 has the Erish-Heilman property with respect to this class is the same as proving that this family, P6, P4 complement, and C7, has the Erish-Heilman property, right? It's just the same thing. Okay, well, one good thing about this family is that if I also exclude the 5 cycle, then I only get perfect graphs, right? Because, so in here, what kind of holes and anti-holes am I allowed? Because I'm excluding a 4H antipath, there are no holes of lengths bigger than 6. And because I'm excluding a 6H path and C7, there are no holes of lengths also bigger than 6. So if I exclude C5, again, all I get is perfect graphs. Also, the 3H path has the Erish-Heilman property with respect to this family, and that's just because the 3H path has the Erish-Heilman property with respect to this set of all graphs. Okay, so then here I am, I'm thinking about a graph in this class, and I'm trying to prove it's it's delta reach for some delta. Well, I can assume it contains this, where this is, I take a 5-gon and I substitute a 3H path for each of its vertices. Okay, so now we think about it, and now again you can prove, well, so let me do it more slowly. Eventually you prove there's a homogeneous set, but let's think about it. So I started with my 5-gon with a 3H path substituted for every vertex. Let me generalize it. Let me just say that each of these sets is connected and anti-connected. So V1, V2, V3, V4, V5. Vi is connected and anti-connected. Anti-connected means connected in the complement. Right, so connected means G, the graph induced by G on this is connected. Anti-connected means the graph induced by the complement of G on this set is connected. Okay, so I can start because the 3H path has this property. Now I can assume somebody is mixed on V1. Well, so here's this guy. It has both neighbors and non-neighbors in V1. Now, so this set is anti-connected. I claim that means I cannot be mixed on this plus that. Why? Because since this is anti-connected, I can find a non-edge between a neighbor and a non-neighbor. If I were also mixed on this, I can find another non-edge between a neighbor and a non-neighbor. And this non-edge is complete to that non-edge. Well, let me draw it separately. So I have two non-edges complete to each other. And this guy is mixed on this non-edge and mixed on that non-edge. That's a 4H antipath, right? I go 1, 2, 3, 4, 5. That's the numbering of the vertices. Okay, so I cannot be mixed on the union of those. So there are two cases. Maybe I'm complete to them, maybe I'm anti-complete to them. Suppose I'm complete to them, right? So check marks means I'm adjacent to them. Well, then I claim I cannot have any neighbors here. Because suppose I had a neighbor here. Well, so let me put my V in the middle. V has a neighbor here, and a neighbor here, and a neighbor here. If I could find a non-neighbor here, that would be a 4H antipath again, right? A 4H antipath is just a square with a head. So if we had a non-neighbor here, then I would take this square with that head. If V is complete to this, then let me take something else. Let me use the non-neighbor here. Let me take this square with this head. So in all cases, I get a 4H antipath. If I had a neighbor here, I get a 4H antipath. So I can assume there are no neighbors here. And similarly, I can assume there are no neighbors here. But now, so what's happening? V has both a neighbor and a non-neighbor in this set. It's complete to this plus that, and it's anti-complete to this plus that. Now I claim I can add it to the structure, right? What was the definition of this set? These are people that are complete to this plus that, anti-complete to this plus that, and this set is both connected and anti-connected. Well, I can add V because V has a neighbor. Since V has a neighbor here, this is still connected. Since V has a non-neighbor here, this is still anti-connected. So my structure wasn't maximal after all. Okay, so that was the case when I was complete to those two. Now, redraw the picture. So same situation, right? Still V is mixed on this. And now we did the case when V was complete to both of these. We proved that V cannot be mixed on this plus that. So now I need to do the case when V is anti-complete to both of them. Well, now I claim V is anti-complete to both of those also. Because suppose V had a neighbor here. Well, now let me use the fact. So far I only used the fact that this set was anti-connected. And so I could find a non-edge between a neighbor and a non-neighbor. Now let me use the fact that this set is connected and use an edge between a neighbor and a non-neighbor. And then what I do is, so let me put V back. So V is adjacent to this and adjacent to that, and non-adjacent to this and non-adjacent to that. That this is a house again, right? This is a foreground and this is a head. Okay, so V does not have any neighbors here. But now I'm stuck. So this is possible. This can happen. Okay, so this didn't quite prove what I wanted. But what it did prove is that if I also excluded this graph, right, a 5-gon in vertex with just one neighbor in it, then I would get a homogeneous set. So if I look at a family of graphs where I exclude P6 I exclude P4 in the complement, I exclude C7, and I exclude that. We prove that this family has the Erdős-Hajnal property. Right, so let's just say the proof very quickly. C5 has the Erdős-Hajnal property with respect to this family. We grow this structure, and now we get a homogeneous set. So this family has the Erdős-Hajnal property. Well, okay, now now what does that mean? That means that this guy has the Erdős-Hajnal property with respect to this family. Well, let me take this guy and grow it. And then turns out you get something else, which I wrote down. You get that if only you didn't contain this, you would be fine. But that means that he has the Erdős-Hajnal property with respect to this family. And so you keep going and going, and eventually you prove that just this family has the Erdős-Hajnal property. Okay, so in case you weren't following every detail, we just proved that every graph in this class is delta each for some delta. Okay, but now we can finish it easily. So, okay, so remember, I'm trying to prove that this family has the Erdős-Hajnal property. At the moment, I know that this family has the Erdős-Hajnal property. In other words, C7 has the Erdős-Hajnal property with respect to this class C. All right, so C7 has the Erdős-Hajnal property with respect to the class. The 3H pass has the Erdős-Hajnal property with respect to the class. So as before, I can grow, I can generalize that structure. Right, so that means this graph, right, C7 with the 3H pass substituted for every vertex has the Erdős-Hajnal property. So if I'm trying to prove that some graph, which is P6 and P4 complement free, is delta each, I can assume it contains a copy of that. Right? That's by our substitution theorems. And now let me generalize this again. So in the same way as before, I'm going to have 7 sets. Consecutive ones are, in a circle. Consecutive ones are complete. Non-consecutive ones are anti-complete, and each of them is connected and anti-connected. Each VI connected and anti-connected. Okay, so now I'll try and do the same analysis as I did for C5, except this time it will work. So let me just show it to you, and that'll be it. Well, almost actually. Okay, so I can assume this is not a homogeneous set, so there is a vertex mixed on it. Now, as before, I cannot be mixed on this union, because if I were, I would get a non-H here I'm mixed on and a non-H here I'm mixed on, and that would be a house. So either I'm complete to both of this or I'm anti-complete to both of this. Suppose I'm complete to them both. Well, then I claim I must be anti-complete to that. Because if I had a neighbor here, then, so here's my V again, this would be a house. Right? This is a foregone, this is my vertex, my extra vertex, and this is a head. So I must be anti-complete to both of those. Now, if I have a neighbor here, I can get a 6H path. I start at V, I go 1, 2, sorry, wrong problem. Try again. If I had a neighbor here, then there's a house like this, right? This is a foregone, and this is a head. So I'm anti-complete to both of this. But now again, I can add my V to this set. It's complete to those two, anti-complete to these 4, has a neighbor and a non-neighbor here, so I can add it, and the structure wasn't maximum. So the remaining case is when I'm anti-complete to both of those. So now, let's see. Sometimes I can do it, yes. So suppose I have a neighbor here. Let's use the fact that I can find an edge between a neighbor of V and a non-neighbor of V because this set is connected. And then, so now here's a house. Right, this is V, neighbor, non-neighbor, neighbor. So this is so far C4, and this is a head. So that tells me I'm anti-complete to this, and I'm anti-complete to that. Now, if I had a neighbor here, then I can find the 6H path. I go 1, 2, 3, 4, 5, 6, going to the known neighbor here. So I'm anti-complete to this, and from the symmetry, I'm anti-complete to that. By now, I can find the 6H path using this neighbor. I go 1, 2, 3, 4, 5, 6. Right? And we're done. So nobody is mixed in this set. This is a homogeneous set. We're done. Right? We know that the minimal counterexample doesn't have a homogeneous set. So this, so this is the proof of this second theorem. Let me just tell you about one more idea in that proof that so just to kind of sum up, we just proved that every graph in this class is alpha narrow for some alpha, or delta each for some delta, right? So which means this family has the Erdős-Hajnal property. Let me just tell you one more idea that it's too technical to actually show it in a proof, but it's kind of important here. So we said if I'm trying to prove, here's a big graph G, and if I know that all its induced subgraphs are alpha narrow and it has a homogeneous set, then this graph is alpha narrow. Well, you don't need quite as much. If you follow the proof of why having a homogeneous, why substitution preserves alpha narrowness, all I needed was that if I take, so all I used was that if I take an induced perfect subgraph here, and I also take some so I also look at the graph where I replace this by a single vertex. So let's call this A, this B. Right, so this is my graph G, and this is the same graph except I replace this homogeneous set by a single vertex. So to prove that this guy was alpha narrow, all I used was that if I take a perfect graph here, perfect induced subgraph here, that uses this vertex, and I take a perfect induced subgraph here, and I substitute this for that, then what I get is perfect. That's really the only property we used in order to say that that substitutions work. Okay, so let's isolate that as an axiom. Right here, I use the theorem of loss to say that that's true because, right, when I substitute a perfect graph for a vertex over another perfect graph, I get a perfect graph. But let's just make an axiom. Let's say a quasi-homogeneous set. So here we said this set was a homogeneous set. Let me say X is a quasi-homogeneous set so I have X and I have some people that are complete to it and I have everybody else. Right? So now I don't know what everybody else is doing because X is not a homogeneous set. And now let me look at a new graph where I replace X by a single vertex. And I make it complete to all the neighbors of X and anti-complete to everybody else. Right? So I replace this by a single vertex. I made this single vertex complete to all the common neighbors of this set and anti-complete to everything else. So let me say this is a quasi-homogeneous set if for every perfect graph here using little x and perfect graph here contained in big X, if I substitute, so if I look at the graph, at the subgraph of this induced by this part plus that part, that's perfect. So it's this thing except I made an axiom out of what I really needed. That when I take a perfect graph like this and I sort of substitute this in, except I take into account all these extra edges, what I get is perfect. Well, okay, so that's still good enough, right? If I could find a thing like that, it would still not be a minimal non-alpha narrow class in the graph. And in fact, in this theorem, actually in the previous step, in this theorem, at one of the stages we don't get a homogeneous set, we get a quasi-homogeneous set. But the same type of proof works. And so let me stop here. Thank you.
Thank you. Any questions?